That have an area of 2 by 2 kilometers. We have more than 30,000 students. We have more than 2,200 international students, and several research groups are working in our university. We have 9 faculties, and I belong to Faculty of Engineering and Technology. In Faculty of Engineering and Technology, we have 3 departments: Department of Electrical, Mechanical, and Civil Engineering. I am from Department of Mechanical Engineering. Here is the scope of my talk. As I told you that I have divided my topic into 2 subsections. The first one is regarding introduction of tidal current energy, then growth of renewable energy, tidal energy research that we are doing in our university, and then about the tidal design and the experimental data that we have, and then modeling of tidal current turbine using CFT and FSI, and at the end the conclusions. When we talk about energy, the population of the world is increasing, and so is the energy demand increasing day by day. The society is faced with the issue of energy and the climate changes due to this fossil fuel usage. According to the World Energy Council, the global energy consumption is 546 exajoule in 2010, and that will be increased by 27% till 2050. So, the ever growing energy demand and the risk of carbon emission associated with the burning fossil fuels are stressing the new need for renewable energy resources. Okay. It is expected that renewable energy will be able to replace the fossil fuel in near future, and many of the renewable energy technologies are growing maturely. In 2012, more than half of the new addition to the global energy are from renewable energy sources. The hydro, wind, and solar energy sectors are witnessing a substantial growth in the world. New concept of renewable energy are also coming into picture, and extensive research is on academia and industry is doing on that. So, tidal current energy is among one of them, and as you know that tidal energy is produced due to the gravitational difference of sun, moon, and earth. I received a message that I have to conclude my presentation shorter, so I will skip these slides. This is the tidal energy data available in Pakistan. These are the classification of the devices which are used to extract the tidal current energy. The horizontal axis turbine is mostly used in R&D, and it have the same principle as the wind turbine have. Other devices include vertical turbine, oscillating turbine, and ducted turbine, some Archimedes screw, and tidal kites, etc. You can see in this chart that 76% of the research is done on horizontal axis turbine. So, this is the most turbine which is used by the researcher in universities. If we talk about the technology readiness level of tidal current turbine, as I told you before that this is an emerging technology. So, we say that this is a technology readiness of 6 and 7, in which we say that only it is available for demonstration or prototype of tidal current turbine is available. It is not used commercially or not installed for commercial purpose at the moment. So, it is in the development stage. Here I will show you some slide in which different universities of the world are working on tidal current energy. Some universities from Sweden, United Kingdom, United States of America, and then Republic of Korea, Singapore, Canada, China, and Ireland are working. These research group are the most famous among the group which are working on tidal current energy. And the topic on which they are doing work are mostly this topic on the resource characterization, device development and testing, hydrodynamic modeling, grid integration, PTO and control, station keeping, mooring, structural mechanics, material fatigue analysis, and the environmental impact and appraisal and operation maintenance and decommissioning of these devices. Now, if I come to the research which we have done or we are doing, we are mostly doing numerical analysis of tidal current turbine. The project mentioned like design and fabrication of horizontal axis turbine, then hydrodynamic analysis of the same turbine, effect of real sea condition on that turbine, and the fatigue analysis is done by our research group. And we are now simulating the effect of structural load on turbine arrays. And one of other students is working on vibration and fatigue life modeling of tidal current turbine monopile structure. So this is the turbine which we use for our simulation. Basically, this turbine is designed and the experiments are done by Department of Energy, USA. They call it reference model 1. So this is a scale down of to 1:40 to the original one. The rotor dia of this turbine is 0.5 meter. This means that the actual turbine is of 20 meter rotor dia. And the blade profile used was NACA 4415, solidity was 13.7, blockage used was 14.3%, and this experimental data was acquired in 2014. So we compare our CFD and FSI result with this data. When come to the CFD modeling, we use ANSYS, and here you can see that a CFD model representing tidal current turbine in the experimental water channel consisted of two domains. One is the domain of turbine that has diameter of 0.7 meter and length of 0.23 meter, and another one is the domain of C, you can say, that have that is in a rectangular channel shape and dimension of 1.375 into 1 into 4.755, and this all analysis was done on in steady state analysis, and rotating frame of reference is used for this modeling. Now, if you see the domain of the turbine, the rectangular domain was in stationary coordinate system, the rectangular coordinate that represent the sea water. And then while governing equation of the cylindrical domain were formed in rotating frame of reference to simulate the rotation of the turbine. Tetrahedral mesh scheme was adopted, and higher mesh density was found around the turbine blades, and in the inner domain the total number of elements was 3.9 million. So here we for this mesh refinement study we use three conditions. All these three operating conditions offer different CFD modeling challenges and is important to study. Like in first condition, we have choose the tip speed ratio of 2.23 that represent an operating condition where the angle of attack is very high, and in this simulation the flow is separated and turbine blade is stalled throughout the simulation. And in the second condition, we have a tip speed ratio of 5.11, that is almost the optimal tip speed ratio for this turbine, and the second one is with high third one is with higher TSR of 9.02. Here for this mesh refinement, you can see that after in the second and third stage it is converge. So we use this mesh density for our simulation. So this is the performance prediction results, and to validate the utilized CFD technique calculated result, we compare it with the experimental data. 8 simulation at different TSR ranging from 1.42 to 9.05 are done in these simulations, and the average difference, or we can say the error with the experimental data, is 6.4%, and the maximum difference is 9.2%. But we are concerned with the optimal value of TSR, and when we look at that data, that difference is very near to the maximum power production. Here you can see that this red triangles show the simulated result at 8 TSR, and the black circle data is of the experimental data that we use from the Energy Department of USA. So here is again, in this slide, we see the effect of blockage ratio on the turbine performance, and we use 7 computational fluid domains with varying blockage ratio and constant depth. Blockage ratio is very important phenomena when we want to model an array of turbine. So we use this simulation for that purpose. And for low TSR, 2.23 blockage ratio has negligible effect on tidal turbines, and CP of turbine increased by 13% for the optimal value of TSR, that is 5.11, and it increased by 47% for high speed or higher TSR. Similarly, we check the effect of CT on the block ratio, and CT is also increases or the blockage ratio range, and that is increases from 8% to 10%. So if I conclude with this effect of blockage ratio, a positive correlation exists between turbine performance and the blockage ratio. The next modeling simulation is to check the effect of boundary layer on the turbine. And tidal turbine are operating in shallow water, and that are expected to operate under some form of boundary layers. For a standalone device, this effect will predominantly be from the seabed. However, if we use an array of turbines, then we have to consider the side effects of boundary layers. So 2 sets of simulation had been performed to check the result of boundary layer. In the first one is with the symmetry boundary condition, and in the second one we use no slip boundary condition, and the second set for the bottom and side wall of the channel. The optimum TSR of 5.11 was used for both set of simulations. So here you can see the presence of boundary layer has resulted in an increase in the predicted performance from the entire range of simulated blockage ratio. And power coefficient of the turbine increased from 2.7 and 3.5%, and the thrust coefficient increased between 1.5 and 3.5%. So here is another effect when you want to model the support of the turbine, or you say column of the turbine. What is the effect of that? We have simulated that effect. Due to shortage of time, I will skip this simulation, but you can see that the rotor torque varies between 2.5% if we see the effect of column of the turbine. Now we come to the second part of the simulation. The first one was on CFD, and the second one is on FSI modeling of TCT performance and structural load. In CFD model, perform rigid body simulation and ignore the hydroelastic behavior of the turbine blades. So in FSI, what we do, we also consider the hydroelastic behavior of the blades. Turbine blades are flexible and undergo significant deformation. The blade deformation needs to be accounted for accurate prediction of the turbine performance. So coupled FSI model are more useful for modeling structure involving flexure or adaptive material. Coupled modular FSI model can also provide structural details. So if we come to the FSI model, there are several techniques, and we use this loosely coupled FSI technique for our simulations. So just to show you in this chart that we do the FE simulation by FE modeler. Similarly, we do the CFD simulation by CFD, and only the forces and displacement between CFD and FE are transformed. Like if you see at this slide, we do the mechanical simulation using FEA, and then we send this displacement to CFD analysis, and from CFD analysis, when we perform this analysis, we get the forces that we give to FEA, and in this way this coupled FSI work. In FEA's, the FEA model which we use is a transition structural component system within the ANSYS workbench. Geometry was shared by the CFD and FEA, Mesh was different than CFD for, and FEA. Blade and hub were modeled as solid. Normally the blade are not solid, but for simplification we model it as a solid material. Structural steel was used. Normally structural steel is not the material which is used for turbine blades manufacturing. Normally it is made of composite material, but for simplicity we use steel structure. So this simplification was required as the model is in the development phase. Simulation, total time and time step were same for CFD and FEA. This system coupling is a module that is used in ANSYS, and so we use this module for coupling. Here are the result of the CFD, FSI and the experimental. You can see that the difference between the experimental and CFD is higher, while if we use the FSI technique it is reduced to 4.8%. Here are some wake study. We use up to 9D of wake for studying this result using FSI. These are the result. Almost the result of CFD and FSI was similar, and the reason was that the simplification which we did, like we used steel structure instead of composite material, and we use solid structure of the blade instead of hollow structure. And similarly the maximum deformation is 0.12, which is very low if we look at the deformation. As I mentioned that we use steel structure, if we use composite material this deformation will be larger, and similarly the other result will have more effect or will be more comparable with the FSI. So if I conclude, coupled FSI model can more accurately estimate the turbine performance compared to the rigid body CFD models, and two-way coupled FSI has been shown that it can be a powerful tool in understanding the critical point in a device design, and with detailed model potential failure points can be identified, as well as areas of our design can be identified using FSI. So these are our next tasks which on which our research group are working. FSI modeling of full size TCT with tower and nacelle included in the model. Blade will be made of hollow with reinforcement webs. More realistic material property will be assigned, and effect of velocity, shear and turbulence on the fatigue life will be investigated. Thank you very much. If you have any question, I am here.